All right, I think we're going. I think we're live. Good morning, folks. How are we doing today? Very good. I hear at least one person is alive with a voice. I'm glad to hear that. I count that as a success. The human race lives on. Aren't we excited? So today it's another coding stream. So for those in the Zoom class, if you can, just throw your name in the chat. Just to make sure that in case your Zoom handle is something weird we don't recognize, we can log you as attended. Okay. So all right. So today we're going to be doing a little bit more coding. Okay, of these simulations of dynamical systems, and this is fun because you get to make animations today. You have to make pretty videos in MATLAB. It's one of my favorite parts of doing control is making pretty videos. So, well, pretty is in the eye of the beholder. For me, we're gonna start off rudimentary, but you can always make them fancier, right? So we'll see how far we get. There's gonna be some animations, but there's also gonna be some actual control systems we're gonna put into our simulation, and we'll see how far we get. I hope to get a little bit of linearization as well. We'll see how far we get during today's lecture. But to refresh yourselves, I would bring up the code that you pulled together at last lecture. Okay, if you don't have it, well, good luck. Guess what? Guess what, friends? You can go onto our Canvas page, and I have uploaded the code into the files page. You go under files, and you'll see tutorial code. There'll be a little folder there with the code from last week. Okay, now we have all this all set up, and then so after every one of these coding lectures, I will just drag and drop the code into that folder so you have access to it. For those who are watching not as part of the class on YouTube, I'm going to see if there's an easy way for me to upload this code so you all can have access to it. Maybe a GitHub link. We're still working on that. A little one step at a time, but should be a good time. So, all right. And for people in the class, we also have homework 1 has been assigned and published. Okay, if anyone's having any trouble finding that, just go into the assignments page. It's also the files are hidden under hidden posted on the files for the homework are also posted on the files page of Canvas. You can find them there too. Highly recommend you get started on it, especially given the fact that these are coding based assignments. Even if you get the concept, sometimes the code takes time to debug. And speaking of which, you're having problems debugging the code. We do have our office hours. They are officially set up for you all. We have spread them throughout the weeks. Okay. Now my office hours are currently Mondays and Fridays. You can look on the Canvas for the exact times. However, I'm going to move my Friday office hours to Wednesdays starting next week, so I'll update the Canvas page accordingly. And the TA office hours are Tuesdays and Thursdays. So 4 out of 5 days a week there is an office hour for you to attend. Okay. And don't forget, if you're having problems with the homework, before you can come to office hours, if you check the homework FAQ page, frequently asked questions. They're up there for reasons because many people ask these questions. Okay, people run into similar issues. So that's also up on the Canvas page. Highly recommend you check it out. So it can be very helpful. All right, with that, let's pull up our code. Does anyone have code from last week in MATLAB? Anyone have it? Anyone successfully put up those pendulums? Yes, all of us. Every single one of us. Glad to hear it. See some thumbs up. Wonderful. Cool. All right, I'm going to pull up my code real quick to make sure we're all good to go. All right, so we've got, I'm going to run. So I'm going to run this. This is the code from last week. This is the sim pendulum code. Okay, and I'm running it by hitting F5, and up pops a little figure. Up pops a little figure. Fantastic. You got time on on the horizontal axis, and you got angle on the vertical axis. All right, and 1 second here. I just got to check something, make sure we're all good to go. And you can see that it's oscillating back and forth. And I did not label these 2 different lines here, so I'm going to do that really quick. Let's see, pull this up. So if I add a label to our plots, I'm going to say, sorry, legend. I believe it's legend, right? Yeah. Okay. And my first label is of, let's see, is of my Euler's method. Euler method. And my second is using ODE 45 solver. I'm going to rerun it like that. And now you have, see in black, we have this Euler's method, which is inaccurate. It is a pendulum that is swinging, okay, and is gaining energy. And we're not putting energy in. That's not good. It's not good, right? So what we need is, and the reason is because Euler's method is somewhat, they're all approximated methods, but Euler's method is a rougher approximation, a simpler approximation of how you actually simulate the system, as opposed to this more accurate ODE 45 version, okay? So that's what we got going on here. So when it comes to what we're going to do next, right now, this is a passive pendulum. Right now, there's no control on it. We're not adding any actuation to it. All right. So how do we change that? Well, let's go to the board. And we covered this a little bit in class last time. Okay. So here we got, let me get new position. All right. Today, 2026 01 22. All right. So we are going to be controlling and animating dynamical systems. Okay. Now, recall that there are two general types of control. Okay. One is the types of control. One we called feed forward control. So we call that open loop. And feedback control. That is closed loop. All right. So recalling that the feed forward control, that means you're just putting in an input and you're not measuring or using measurements of what's happening to see what happens, right? To adjust what's going on. All right. That basically you send in that signal, that control signal forward, okay, and then something happens, right? So let's say we have our example system, okay. Again, it's the pendulum, just because we've already coded it up, okay. The pendulum, okay. So we got our pendulum, got a little stick, got a little mass. It's sloppy even for me. Let's make this a little nicer. Speed, I guess, is the name of the game for me. We're speed running these lectures. Let's slow it down, get nicer handwriting. Okay, you've got the length of that pendulum, L. You have a mass, M, and G. Now, what we do not have currently is a torque on this pendulum. Let's put a torque on the pendulum right there. Let's call it tau of T, okay? And we, of course, have the angle of this pendulum relative to the vertical is theta of T. Now, we very briefly derive these equations in the last lecture, and just as a recall, is that if they are theta double dot of T is equal to minus G over L. Actually, we didn't do it for the pendulum. Sorry, we did it for the mass spring damper. But it's a very similar process here. We added an external torque. We would do our free body diagram, summing all the torques about this point here. Okay. And it will become minus G over L sine of theta of T plus tau of T, which is your torque. Let me write that out. It's a motor torque. Okay. Over the quantity ml squared. You might recognize this from physics, that is the moment of inertia of the rotation of this mass about this point right there. Okay, so you divide a torque by your rotational inertia, you get your angular acceleration. Oh, good. That's what we have right there. Your theta double dot is your angular acceleration of your pendulum. Okay, so if we add in a torque to our system, okay, then hopefully the system will behave differently. Okay, now one thing though is once we start, let me go back to my code here. One thing I would like to change a little bit. Right now, when I run my code, it gives me these plots, right? And these plots might be intuitive to you, or they might not be as to what's happening. This is an angle over time. It's swaying back and forth, right? It can be helpful to animate what's happening for a physical system in order to know if it's working right, just to give you a hint, right? And also give you a little intuition as an audience member to see what's happening, right? So what we're going to do is we're going to throw an animation together very quickly of this pendulum so we can watch what's happening. All right. Then we're going to put a controller on it. So let's make an animation. So make an animation. So let's animate our system. Okay. Okay. Let's animate our system. Now, an animation, all it is it's a bunch of images played in a sequence. And you play them fast, it looks like they're moving. That's all it is. Well, in MATLAB, we're going to take a plot, and we're going to plot it, and then we're going to plot it again, and again, and again, and again, with the pendulum in different positions. And then it looks like an animation, so we can watch what's happening. It's that simple, really. That's all it is. It can get much more complicated when you want the animation to look fancier, but if you can plot something, and you can put it in a loop, you can animate, all right? There's a couple little tricks along the way that I'll show you, all right? So first thing, we need to design an animation scene. Okay? And so here's how I'm going to design it. I'm going to design it by saying that here is the hinge of the pendulum. That's at point 0, 0, the coordinates 0, 0. Okay? Now here is the bob. So this is the joint, the hinge, the pin joint. This is the bob in some position. Currently, I'm just drawing this vertical angle, right? Okay? And this is the angle theta of t, right? So what we need to be able to do is that when the pendulum is at a certain angle, theta, let's say it's at 45 degrees, right? We have to be able to tell the plotter to plot this at this line at 45 degrees. We'll make our scene really, really simple. Just a line, okay? The pendulum's just a line. We don't even draw a circle at the end yet. We can add it later. So in order to plot that line, all we have to do is know what these 2 points are, right? This one, I'm saying the hinge is at 0, 0. This one, I'm saying the bob is where? Well, it depends upon it depends upon our angle theta. So to figure out what that line is, where that line is, we're just going to do a little bit where this point is. We're just going to do a little trigonometry, knowing that the length of the pendulum is L, and this is the angle here theta, right? That's L. Therefore, the length of this line, that's going to be L cosine of theta. And because X and Y are going to be pointed to the right is positive and up is positive, and this is going down, L cosine theta is going to be minus L cosine of theta. Okay? And here we go. We have this is the opposite over the hypotenuse, right? So that's going to be L sine of theta. This line here, L sine of theta. Okay. Of t. So whatever angle we're at, we now have the XY coordinates of that bob. That bob is going to be at L sine of theta for the horizontal axis. And for the vertical axis, it's going to be minus L cosine of theta. Just some trigonometry. That's all it is. Not bad, right? Not bad. Now with that, let's plot. So now we know the two coordinates to plot on a line for a given angle theta. Okay, so let's go back to our code with this in the corner. Those are our. So this is just the code from last time. I'm just adding to it. I'm going to create an animation of the pendulum. And we're going to discover a few little glitches along the way that we're going to fix. All right. Okay. So right now, our output of our simulation, let's just say for our ODE 4.5 simulation, it stores all of our time points in a time vector, and it stores all of our states in this matrix of states outputs. In fact, what I'm going to do is going to show you what's in X out. Okay, in X out, it's got two columns. Each column is a state, and each row is the next time point, and the next, and the next, and the next. You can see it has all those different time points down below. See that? Okay, where the first column is the first state, second column is the second state. Now recall that we defined our states. Let's put it over in the corner here. Our states were theta of t and theta dot of t. So if we want access to all of our states, for all of our angles, we want that first state right there, which is the first column. And the way we said, hey, we want access to that first column, we say, hey, X out, we want every single row and the first column. The colon is every single row and the first column. So if I were to go into the command window, I'd say X underscore out, every single row and the first column. Sorry, I'll go back and show you. You can see that you can, let me write that out again. If you hit enter, you'll see that's the entire first column. Those are all of our angles. Okay. And at what time points are there? Are they at? We'll look at T out. T underscore out is what I called it. You hit that, hit enter there. You can see what comes out. Look, there's all your time points. Boom. Right? Now, who decides these time points? In this case, it was ODE 4.5 that decided what those time points were. Because as we talked about, if with Euler's method, there's in other time marching integration algorithms where we choose the time step, it's up to us what we chose what it is, and can be constant. But ODE 4.5 can make it small or large over time, depending upon what it thinks will make more for a more accurate simulation. Okay, so those are the different time points. So this is how we're gonna know what time where the pendulum is at. So let's just create the animation drawing just the pendulum at the first time point. So what we're gonna do is we're gonna just do a new plot, and to make a new plot, I'm just gonna say figure. Figure is going to open up a new plot window. All right. And I'm just going to do a plot, and I'm going to want to plot my X coordinates in a vector and my Y coordinates in a vector. Okay. And I'm going to connect them with just a black line. Right now it's just open close just because it's empty. We haven't decided we haven't written exactly what we want to do for our different points. But for our two X points in our line, what is the first horizontal X point? Well, let's start at the hinge. It's this 0 right here. Okay, so 0. All right, what's our second one? It is L sine of theta, right? And let's just plot the very first angle that we have, okay? The very first angle, so that will be L times sine, and our very first angle, meaning that just the angle at the very start of the simulation, is going to be the first row of X out and the first column. Okay, so let's just say x out 1, comma 1. Voila. All right. Now for our y coordinates. Well, our 0 is, we'll start with 0 for the y. And now we want, for our second y coordinate, minus L cosine of theta. Okay. Minus L times cosine of theta. And we're just going to do the very first time point. So it's going to be the first row and the first column. Okay. There we go. Any questions so far? Kind of basic, just some trig. We're just whipping around here in the morning. What could go wrong? Okay, I'm going to plot that. I'm going to run it, and it creates a second figure. Hey, look, it's a line. I'll shrink it down so you can see everything a little cleaner. You can still see the code right there. There you go. It's a line. Okay, we did it. We plotted a line. Now, is that roughly right? It actually is roughly right. If you scroll up to whatever our initial angle was that we decided to drop the pendulum at, where do we define it? Where do we find it? Pi over 4. Pi over 4, that's 45 degrees. Now, you might say, that doesn't quite look like 45 degrees, and you might not be able to see it. So what we're going to do is we're going to make the line thicker so you can see it over Zoom a little easier. So I'm just going to make a new line here, and then a new line here. And I'm going to say, hey, I want my line width to be 3. This is pretty darn thick. It's a pretty thick pendulum. All right. Now run it again. You can see that line probably a little thicker, right? Does that look like 45 degrees? It may or may not. It depends on how you shrink the plot, right? So we can squish the plot so it does or does not look like 45 degrees, but the position is probably right. But I don't like the fact that when you squish it, it changes what the angle looks like. And the reason that is because when I stretch the plot, MATLAB tries to fill the plot window as much as it can, and it'll end up stretching your animation. I don't like that. I don't like that. But there's a simple command that I love for animation specifically when you're looking at a physical scene, okay? And it's called axis equal. It's beautiful. I love it. Because what it says is that, hey, it says I want on the screen 1 unit in the horizontal axis to be the same as 1 unit on the vertical axis. Meaning if I stretch my plot, it will always keep those axes the same, so that way it doesn't distort the angle, okay? So I'm going to hit axis equal, I'm going to rerun it, and look, there is my new plot. And if I stretch it, that's 45 degrees. Perfect. All right. We've drawn 1 frame of the pendulum. Now we just have to loop it and draw it for all the different time points, right? Okay, so let's start with that. So so we need to make a loop. And there will be a slight flaw with this loop that we will fix in a second. I just want to make it clear why. So we're going to do a loop, an animation loop here. So what that means is we want to redraw that pendulum at all of our time points. Astute observers will know there'll be a slight flaw, but it's okay. We'll fix it in a minute, right? So we say for some iterating variable for the number of times we want to iterate is equal to 1 colon however many time points there are in our time vector. So let's say num L time vector. So T out, that's number of elements. EL, not E1. E out. Okay. Okay. I'm going to put a little end loop here. Okay. And I don't want to just plot the first time point. I want to plot the iterative time point. As iterations go through, I want the next row and the next row. Iter. 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 Okay. All right. Technically speaking, I would like to indent. It's not unlike in Python. Indentation doesn't actually technically do much or anything in MATLAB. But to make it look nice, I want these two inside the loop indented. So what you can do is you highlight the section you want to indent properly and hit Control I on my Windows keyboard. It might be different on a Mac. Control I automatically indents. Look how nice that is. All right. So now, if I run this, what happens? It's going to run. It didn't animate anything. It just showed me a plot. That's because MATLAB will not draw the plot until it thinks it's done drawing everything. So we have to tell it to draw the plot at the end of each iteration of this loop. We use the command draw now. So we just add the command draw now at the end, and we're going to run it again. Okay? Now watch it. Okay, something's moving, right? Not pretty, and I'm not sure it quite looks like a it sort of kind of looks like a pendulum swinging around, but the camera's going all over the place. It's shrinking around, right? Let's fix that up, okay? So basically, because it's being redrawn every iteration, but the axes are changing. What I want is I would like it so if I'm just looking at the same sort of framing of the camera, if I'm looking at a camera through this pendulum, every single frame, which means I want to set the axes to be constant. I don't want MATLAB to choose them for me. So what I'm going to do is I'm going to say, hey, I want the axes, and I say axis, open parenthesis. I want my horizontal limits. I will set my horizontal limits to be the length of the pendulum to the side, to one side or the other, plus a little bit. So I'll say I want it to be minus L times, I don't know, 1.25. Gives me a little bit of extra space on the left side of the pendulum. And then positive L times 1.25 on the right side. These are the limits of our axis, okay? And we'll do the same thing vertically as well. So we're going to do minus L times 1.25. And then positive L times 1.25. Okay. Now if we rerun it, it should be the same sort of frame over and over again. Here we go. Let's watch it go. There you go. It's moving. Okay. Not bad, right? Any questions so far? Hopefully not too complicated. All right. Good. So, excuse me, take a swig. Question. Mine is going very fast. Is there a way to control that? Yes. Yes, you can slow down the pendulum. And also, the timing of this pendulum is also not quite right, probably. Okay. You'll notice that I am, so we are ignoring an important element, which is the timing of this pendulum. We're just grabbing whatever time points ODE 4.5 gave us and looping through those, right? But ODE 4.5 chose those for accuracy, not for the frame rate we would like to watch the video at. People know the concept of a frame rate, right? When I'm looking at a monitor right in front of me, theoretically, it's flickering at me at about 60 frames per second, maybe 120 frames per second. If you have a special monitor, I don't know. I'm not a monitor guy, but which you choose that based upon what you want to look at, as opposed to the dynamics of the pendulum, which ODE 4.5 is working on. So it would be great if we could, instead of using the time points that ODE 4.5 chose, we choose our own time points. Okay? And so what we can do is establish that we want a certain FPS, or frames per second. And let's just say 20. 20 is a decent animation frames per second. This is animation frames per second. Okay? And instead of having a time out from our simulation, let's create a new vector called t_anim, which is our animation time, which are our animation time points. Okay? So what we could say is that, hey, we want to start at time 0. We want to end at the very, very last time of our simulation, t out, but we want to have consistent increments of time at the frame rate that we want. If this is the number of frames per second, 20, okay, then that means that between frames, that's 1/20th of a second, or 1 divided by 20. In this case, 1 divided by FPS. We're going to increment in that with that increment, and then now we're going to end at the very, very last point of our simulation, time out. So what we can say is we want t out, and we want the very last element, t out, open, close, end. All right. If I put this into the command window, you can see what this makes. Okay, I didn't define FPS, so it's 20. You can see what it'll make is it will make a vector, in this case a row vector, that counts up 0, 1/20th, 2/20ths, 3/20ths, all the way up to the final time, which we had sorry, in the code, we decided was 10 seconds. Okay? Make sense? Okay. So now we need to find what is the angle at each of those time points. And now we're just going to use one of the tricks that's just maybe one of the slightly more intuitive, counterintuitive tricks in our code here. I'm going to put a little semicolon on here before we finish so I don't forget. Okay, let's go back to my board. So what's happening with ODE45 is it is giving us a simulation of some state x of t over time. And it is giving us different time points for our simulation that might look like this, right? In fact, let's plot them as such just really quickly. I'm just going to throw up a quick plot on the MATLAB, not even in the code, just in the command window. So if I were to say plot t underscore out, x underscore out, I want to plot my my angle over time. So I want every row in the first column, and I just want to plot the points, not lines connecting them. So I'm just going to put big black circles. So KO will be big black circles. I make them big so you can see. So I'm going to change the marker size. I'm going to make it 15. Okay, I'm going to run it. I have to close all my plots because it's not showing up. Close all. Okay. That's those little points here. That's what you're getting back from ODE45, right? And when we're plotting it, the lines are just connecting those points. There are lines connecting all those points, right? So when we are animating, we want to, like, if let's say that O is a little big. Let's make them X's. X's. Just to make it a little easier to see. You have all these X's. Now, if you want to plot where that pendulum is at say, let's see, I'm going to zoom in here. At this time, like 6 seconds exactly, what are the odds that we actually have a data point at 6 seconds? We don't, right? I've just zoomed in. You can't quite see. There's a gap here right at 6 seconds. However, I do see an X here and an X here. Now, imagine if I connected these with a line, I could guess roughly where the point is at 6 seconds and get that and use that to animate my time point. Okay, so what we call that is interpolation. Okay, and specifically this is called linear interpolation because we're drawing a line between point and point. All right, so if you go back to the board here, these are our data points. You can imagine them connected by lines, but if we want to know, approximate what is the data point here, even though we don't have one, we just look at these connected lines and we say, hey, if we drew an imaginary line from there to there, this is where it intersects the point that we want. Okay, we could do the math for that. It's just algebra and lines to say, hey, this is point 1, this is point 2, this is where I want, therefore that's the point. However, instead, MATLAB has built-in functions for what we call interpolation. Okay. So and specifically the command that we want in MATLAB, let me put this up here, is called interp1, INTERP 1 for a one-dimensional interpolation, because you can do higher dimensional interpolations as well. Okay. All right, interpolation. Okay, 1D data interpolation. It's a table lookup. Okay, and you give it X values, Y values, and the X values you want to query, XQ. Okay, so in the context of what we had over here, here are all of our X values for all the data points. Here are all the Y values for all the data points. Here's the value we want to query at X, and then it gives us the value of Y. And we can do that for many, many data points. So what I'm going to say is in our code, we're gonna have our angle animations, our angle animation points, or angle anim. Okay, we're going to interpolate on the data that was given to us from the simulation. So our horizontal data is our time, so t out. Our vertical data is the angle. That's going to be x out, the entire first column. And the time points that we want to, look, it's finishing it for us, right? The time points that we actually want to check at and get approximations are our animation time angles, t anim. Great. Now, we can, instead of trying to animate over the t out, the simulation time points, we want to animate over our animation time points. So we're going to change this to t anim right there. And instead of plotting our angles from our vector, okay, for coming out of the simulation, we now have our angle animation points right here. So I'm going to change this theta here. Gonna get rid of that. Gonna change this theta here. Get rid of that. Now this is just a vector containing all of our animation angles. So we're going to say angle anim, and in that vector we want the iterth element, depending upon what iteration of the animation loop we're in. Angle anim, open, close, iter. Okay. I'll leave that up, but I'll run it. There we go. So we're actually setting the frame rate of that. Now, that might be running faster or slower on your computer currently, because if your computer is super fast, it's going to just plot these angles as soon as the computer is ready to do it. Ready to go. But we want it to actually wait the amount of time that you're waiting between frames to redraw it. Okay, and this is what someone in the chat asked, can you slow it down? Yes, there's a command called pause. Okay, if I type pause in a command window, what it does is it waits to press any key in order to continue. So if I hit enter, we're done with the command. Or you could say pause 5, and that's the number of seconds it will wait to do anything else. So if I say pause 5 and I hit enter, 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, and boom, done, right? So if we instead wait the amount of time between frames, which is 1 over our frames per second, so let's add a new line here, pause, 1 divided by frames per second, FPS. This will slow down our animation to make sure that it's running at something close to, not going to be exact, something close to our actual animation frame rate. So if I run this now, here we go. It's running a little slow for me. Could be because my computer's old, or sometimes when you run MATLAB a second time, it'll compile faster. Can I show the angle anim again? Absolutely. 1 second. Let me show that up. There you go. I'll run that one more time. Okay. Now this is just running in real time on the computer. Okay. But for your homework, and it's also just generally helpful to have for any kind of work you're doing, excuse me, it's nice to have a video file of these animations, and you can store a video file. Okay. All right. So we'll get to that in a bit. So you can actually create a video file and store it. But for now, we have an animation that we can run. All right. If you want the animation to be finer, so it has a better frame rate, you can change the frame rate up to 30, or I'll just do 50 just because I can. Okay. There you go. Cool. Very simple animation. Mine's chugging slow, probably just because it's just I'm going to get rid of this this pause command just for me. I'm just going to hit Control R to comment it out just so it runs faster. And where is my command window? I'd like my command window back, please. Command window. Thank you. Good. Control C to exit out of all this stuff. Control C. Good. Look how smooth that is. I love it. So we can now animate our pendulum. So now we can watch what's happening. Has anyone else got an animation going? Any thumbs up for animations? Great, some animations. Glad to see it. So now let's do some control, because right now this is just a swinging pendulum, swinging around. Now let's do some control, because right now it's just swinging. Let's add a feed forward controller, meaning we just have some tau of t that we're going to add in. Okay, so what I'm going to do is I'm going to apply a constant torque to this pendulum at the hinge joint, which means I'm going to have to change my equations of motion. So I have now a tau that I'm going to add in. Okay. Okay, and I'm going to go back to my code. One thing I'm going to do now is I'm going to save a copy of this. I'm going to save a copy, just use save as. I'm going to call this sim pendulum control. That way I have a different version that has the controller on it. Sim pendulum control. Sim pendulum control. I'm going to change the title. Sim pendulum control. And here on this 22nd. Okay, with all my friends. And our equations of motion here are, where are they written out? Yeah. Here are our equations of motion for the ODE 45 simulation, right? We no longer need, as far as I'm concerned, I'm going to get rid of all of this Euler step stuff. I'm going to, everything for me from line 14, which is where I'm simulating using Euler's method, I'm going to get rid of, because I don't want to confuse our plots, and going to erase everything between defining our parameters and using ODE 45 instead. Okay, we're getting rid of. And further, I'm going to get rid of in the legend this Euler's method here, because we only have just the ODE 45 solver. Sorry, got a little bit of an allergy situation going on. Okay. All right, so if I run it, let's see, what did I screw up? Okay, theta 0. Did I screw? Oh, I got rid of theta 0. We'll rewrite theta 0. We'll say here's our initial conditions. All right, theta 0 equals pi over 4. And d theta 0, which is our initial angular velocity, we'll say is 0. Okay, if we run that, hopefully that all works. It still works. Great. Awesome. Cool. So now we want to add to our dynamics this control here. Where is our control? Here we go. Here's our equations of motion. What we added on is this tau of t over ml squared. And that will show up in our acceleration, which is written right here, minus g over L sine theta, plus tau of t, which let's define right above it. Say tau is equal to 1. This could be in Newton meters. It's a torque. Tau divided by quantity m times L squared. Okay, now let's watch it move. And I'm going to change my frame rate back to 20 for me. Okay, I'll keep that back up. Plus tau over ml squared. Let me run the code. You'll notice that it's still swinging. Apologies. It's still swinging. I'm going to grab a tissue. I'll be right back. I apologize. So just hang out, watch the code, watch the pendulum swing. Let me run it one more time. I got to grab a tissue. So we're back. We added it. So you'll notice that it's swinging around, but it's not swinging around symmetrically. That's because the torque is actually pushing the pendulum forward a little bit, but it's not swinging. So it's swinging forward and backward, but sort of offset. It's sort of swinging. The center point of that swing is moved a little bit, what was that, counterclockwise, right? I mean, we're applying a counterclockwise positive torque. That makes sense. So if I change my torque to 2 and rerun it, you can see it's going to shift even further counterclockwise. I'm going to make it bigger. I'm going to make it 5. Let's see what happens. I have to if you need to exit out, just hit Control C in the command window here. Okay. Here we go. Even further. If I change it to 5 Newton meters, and eventually, if I make this big enough, I make it 15. There you go. It's going crazy. Makes sense. We're just applying this constant accelerating torque to it, and eventually it's continuing to accelerate. It only looks like it's decelerating due to the frame rate of the pendulum. There's a little bit of what we call aliasing there. Okay, but that's what happens. So we're going to apply a torque. That's that torque that we're applying. That's a feed forward open loop torque, because this is not in any way dependent upon the angle of the, excuse me, not dependent upon the angle of the pendulum or anything that we're measuring, right? But let's say, my friends, we want to swing that pendulum from the bottom to the top, and we want it to stop. We're going to need a feed forward controller. Okay. We just made a feedback. We need a feedback controller. I'm sorry. We just made a feed forward controller. Okay. Right there. We added a feed forward controller. It can be, right now it's just T equals 1 Newton meter, right? If I wanted it to be something else, if I wanted it to be some time varying signal, let's just say we want it to be a sine wave. Sorry, just do a quick sine wave. Let's say we just want our tau of t to be equal to some amplitude times sine of t, so that we're adding a torque that kind of sways back and forth of some amplitude. We can absolutely do that. Okay, how would we do that? Let's just go back to the code real quick. So in our dynamics function, you'll notice that our accelerations are dependent upon our current state. Our derivatives are dependent upon our current state and t, time. So instead of tau being a constant, let's just say it was sine of t times some, I don't know, big number. Let's make it 15. So instead of tau, we just put 15 sine of t. And I'll rerun it. Woo. It's still going crazy. So maybe we'll do 15. Oh, no, it's kind of going back and forth. Yeah, it's going back and forth. Look at that. We're swinging it back and forth. Anyone getting that? Anybody getting the swinging back and forth? Anyone need to see any part of the code again? Okay, some people are getting swinging back and forth. Good, good, good. Glad to hear it. Awesome. Okay. So, swinging back and forth. Awesome. So that's a feed forward controller. But what we want to do is add a feedback controller. Add a feedback controller to swing the pendulum up and stop. And for that, we're going to use a proportional derivative controller that we're just going to design by hand. And to swing up the pendulum, so we want to start here and then have it go up here. That's an angle of pi. Okay, so we have our desired angle is pi, and our desired angular velocity is 0. And this is in radians. This is in radians per second. All right, and a proportional derivative controller is one where we take our control input, tau of t, and it's going to be proportional to our error and proportional to our derivative of our error, or error dot. Okay? And because these two constants can be different, we'll call this one Kp, call this Kd, and they are both called gains. Who chooses those gains? Currently, we do. But in theory, we can have an algorithm select them for us. But by what metric do they select it for us? By a cost function that we choose. At the end of the day, we're choosing stuff. We're engineers. We're engineering the solution. Okay? All right. So now the error, you'll recall, is equal to your desired minus your actual, D minus A. Okay? Where you want to go versus where you are right now. So this can be our theta D, theta desired, minus our theta actual, theta of t. And the time derivative, d error dt, is the derivative of both of those things, which if this is a constant, by default it's 0, but we've also said it's 0. Okay? So we'll just say theta dot desired minus the derivative of theta with respect to t, which is theta dot, right? So that means that our PD controller, our torque, is equal to some Kp, which is a proportional gain that we choose. Okay. Theta desired minus theta actual plus Kd theta dot desired minus theta dot actual. Okay. We just substituted these things into there and that thing into there. That's all. It's just substituted them in. Okay. So that means that torque command we had, which used to be this 15 sine of t, we're going to change back to tau. Okay. Right. This tau is going to be equal to this command right here, this little line of code. This little equation right here. Excuse me. Okay. So let's put it in there. We have to define a few things. We have to define Kp and define Kd. I'm just going to arbitrarily choose Kp as being 10. I'm going to choose Kd as just being 1. All right. We're doing a little hand waving in terms of the design of the control here, but we just want to get the control in the code so that you can. So we're going to replace this tau again, and this is going to be a longer line, so I'm going to do a little ellipsis to add us a new line. Okay, and instead of tau, I'm going to put in a quantity here, and it's going to be Kp times theta desired, which we also did not define, so let's say theta desired, theta underscore desired, which we said is pi. Right? So that's theta desired minus your actual theta. Right? And our actual theta is in our states, it is our first state, so we would say x1. x1. Okay. There you go. There's our error multiplied by Kp. Now we have to add in our derivative term, which is Kd, which is multiplied by our desired theta dot, which is 0. Let's write that as a variable, though, so we can change it. Theta, so we'll call it d theta underscore desired. We want that to be 0. Okay? So let's write d theta desired. And then we have to subtract it from our actual theta dot. Now, that is our second state, right? So if we go to our code, instead of x1, it's going to be x2. So that should be our controller. All right, I think we got everything there. I'll leave that up for a second. I'll scroll down. I'll try running it, see what happens. Oh my goodness. Hey, let's watch this. It's swinging up. It overshoots. And it's coming back, and it's sort of settling down, right? Look at that. Okay, it didn't quite get all the way there. But if we change the gains around, it might get there better. Anyone getting this? It's pretty cool. We made a controller. So now, as a general rule, if you take controls 1, okay, that the derivative gain, its job, it's acting like a damper. It slows things down. So if you want to slow things down more, you make it a tighter damper. How do we do that? We change the KD gain to be bigger to make it tighter. My animation has stopped moving. Can you rerun it and does it animate again, Conrad? Or did it stop in the middle just like because it hit 10 seconds? So I'm going to change that KD to 3. Make it bigger to slow it down more. Stays at the beginning frame. Okay. Is it still running? Is it still running? So I changed it to 3. Okay, I think I changed KD to 3, and it kind of sticks there. Okay, so the question is, Conrad, can you get it to the point where if you set the torque to be 0, does it back to 0? Does it just swing like it did before? That's what I would check, Conrad. Okay, see if it or if it's something that got screwed up with your actual animation code. Yeah, plotted graph looks right, and it's not animating. Are you sure that you are iterating to a new angle anim iterate instead of 1? I don't know at what point you got it screwed up, what you added when you got it screwed up. So I changed it to 3. It no longer overshoots. Goes a little too slow though. So I'm going to change it down to 2. See if that's sort of like the Goldilocks number here. If that's just right. You can play around with this yourself, right? You're tuning the gains is what we call this. You're tuning the gains. Okay, now it overshoots a bit, blah, blah, blah. We can make KD bigger to slow it down again. You make KP, and it forces it harder toward the solution. So if you make that bigger. So I made that 20. See what happens. Still too much. But you can see it's almost behaving like a spring damper. It kind of springs it up and then slows it down, right? Yeah. Let me know if that helps, Conrad, if you need to fix it with your computer. Okay? There we go. We made a feedback controller. Any questions about that so far? Okay. So we were able to put a controller right here it's a feedback control loop. It uses the current angle, the current state, which is the angle, and also the angular velocity to slow down the pendulum. Now, how did I know to do a PD controller? How did I know to choose these gains? Look, I'm a controls professor. I've done this a few times before. I got a pretty good idea for how to choose the gains. As a general rule for mechanical systems, this is a general rule, rule of thumb, if you will. Not hard and fast, but the higher you make key P, the more it's like tightening a spring between where you want to go and where you are. So we'll try to get there faster. So if I make this like 50, you can see it's going to like really spring up. Wow, 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 right? And then the KD slows it down. But there are better ways to choose this. We are in an optimal controls class. We can actually define the optimal way to do it, okay? But to do that, so there are many approaches we'll learn in the class. One of which, though, is by linearizing our system and using what we call LQR. So right now, these equations here, are they linear or nonlinear? They are nonlinear. Look at that sine of your angle right there. Okay? That sine of your angle. It's nonlinear. But if your system is linear, we have excellent tools to design controllers for your system. That, in fact, if we make our system linear, we can have an algorithm choose our KP and our KD. All right? But we have to make our system linear first, and it will be an approximation. All right? So another thing I'm going to do real quick is I'm going to change our desired angle. Instead of pi, which is up, I want it to go down to the bottom, okay? I want it to go down to the bottom and stay there. So I'm going to change that angle to 0 and show what happens. Okay, change the angle to 0. Voila. It goes there and it kind of sticks there. I'm going to change my gains back to, I'll do 15 and 3 just to have them here. 15 and 3. Not bad. I think let's do a higher KD. Let's go 5. I wanted to just go there and stick the landing. And just go, phew. That's what I want to do. Change it to 5. KD to 5. I want it to stop faster. Okay. Better. I'm going to change it to 8. I want it to stick faster. Hey, pretty good. 15 and 8. With a desired angle of 0. Not bad. How do we linearize a system? Okay. We might not be able to do this in code today. Okay. But we can show you how to do this on the board. Okay. So let's go to the board. So, boom. Oh, I want to do one other thing before we finish here. We didn't turn this into a video, and we didn't. We might have to. We'll save linearization for the actual textbook, the in-class lecture. Maybe just touch on it just a little bit here, because I also do want to. I also do want to show you how to make a movie of your animation. So let me pull that up real quick. Video writer. Okay. All right. So let's pull this up, back our code again. So let's say we want to take this animation, and instead of having just a swinging pendulum on a plot, we actually want to make a movie file that we can play. Okay. What we can do is we can create a video writer to create a video file. Okay. Now here is the syntax for that. Okay. We're going to create a video writer object we call V. All right. This is something you just look up online, and also the FAQ and the homework shows you how. This is built into MATLAB, something called the video writer class. So you say V equals video writer, where V is just the name of a video writer object. Okay. It's a little bit of a detail. And what you do is you define a video writer that's going to write a video to a certain file name. Let's call it animation.mp4. Okay, I want to make a little MP4 file. And I can set the file type, and I highly recommend this, to MPEG-4. This will save a lot of file space. If you do an AVI file, it'll be huge. You don't want to do that. Okay? All right? And you can set a lot of properties of this video writer, one of which is video writer dot, I think it's frame rate. Let's see. Make sure we get this right. Yeah, there you go. Frame rate. Frame rate. And that could be the FPS that we've already decided. Okay. Apologies, I'm pulling up the syntax real quick. So, then you want to open the video writer. You can say open V. This opens the video writer. All right. Now we've opened the video, and then every time we have a frame that we have drawn, we want to say our current frame is equal to get frame, and GCF gets the current figure. Okay, so this gets a frame of the animation. Okay. All right, and now you can write to the video. You say write video V, and you can write your frame to it. Okay, and then when you're done, you say close your video. Okay, so So it gets the frame, it writes the frame, and closes the video. So if you run that, cool. It ran the animation, but you'll notice in the corner of my screen, I'm not sure if you can quite see it. Yeah, perfect. You can see it. There is an animation.mp4 file that showed up in my directory. Okay, so I'm going to just quickly pull up my directory. Second here. Computer's being slow. Boom. So I have my animation. We'll see what happens. See if it actually made it. Here we go. Boom. Look at that. I have a video file. See a question here. Does this save video time every time you run the code? It does. It does save video every time you run the code. So if you don't want it to do that, one thing I like to do is put all of my commands associated with making the video, such as open the video writer. I put it in an if statement. So I'll show you, this is a good trick to do in your homework, okay? So what I do is at the very top of my code, I'll make a little, I'll make a variable I'll call save video, and I'll say it's false, okay? And then I'll say, anytime any of these commands where I do anything with a video, I'll say if save video, it'll run the command. These things in here. And same thing here with this open video V. So it's just end. So I'm literally taking every time I have something associated with the video writing to a file, I put it in an if then statement. So that's creating the video writer. And now this get frame, I say if save video, end. And then here I say, for the close, I say if save video, end. Okay, so everything is bracketed. You'll notice that I have bad indentation. So I'm just going to select everything in the file with Control A and hit Control I to indent it properly. Okay. So right now, if I run it, save video is set to false. So it should just animate, but not make a new animation. But not make a new file. But then if I change save video to true, it'll make a new file. Okay? Now you can make cool video files. But right now, this pendulum, it's not looking cool enough for me. No, friends, it's not. Let's make it look a little cooler. All right, let's add a little bob, a little circle on the end of the pendulum. Well, we can absolutely do that. So let's add a few things. So right now, we're only plotting one line. Let's plot a line and then plot a circle at the end of that line. Okay? We're going to plot multiple things. It means that we're going to have to hold the plot on. So right in the animation loop, I'm going to put a hold on. And after we're done plotting all our things, I'm going to say hold off. But because we're holding things on every time we want to have an animation, watch what happens when I run this. I'm going to turn the animation, the save off. I don't need to save anything. So false. Okay, I'm going to change. I'm hitting Control Home and Control End to go to high and low in my code. Okay, I turn the save video off. I put a hold on and a hold off. Watch what happens, friends. Look at that. It's keeping all the different lines that it's drawn, right? We don't want it to do that. Okay. Also, I don't need 10 seconds of animation. I'm going to change it to 5. Where's my final time? T-final, change it to 5. It's right at the top. T-final, changed it to 5. Change that to 5. T-final equals 5. Run it again. We don't want it to save all those lines. That's what we need to do is clear the frame at the beginning of every iteration of the loop. So you can say clear figure, or you can say clear current axes, whichever one you want. CLF works fine. Okay, look at that. So now we're holding it, but we're also clearing it. So if we wanted to add another, so right now this is drawing the line. Now we want to draw the circle. What do we need to do? We need to find the point of the circle that we want to draw right here. It's the bob right there. And it's at minus L cosine of theta, L sine of theta. So if I plot just a single point, it's going to be, oh, it's L sine of theta. It's this right here. I'm going to copy that right there. Okay. And then that's your X point. New line. And your single Y point, it's going to be minus L cosine of theta. Going to grab that. I'm going to copy that. Does it need to be in square brackets? No, because it's only a single point, but just for consistency's sake, I am. I'm going to make it a red circle. R0. R-O, sorry, R letter O. Okay. And I run it again, and you can see there's a tiny little red circle at the bottom, right? If I want to make it bigger, I can make the marker size bigger. Okay. So I'm going to marker size. I can also change the marker color. Let's make it 15. There we go. And if you want to have it fill with a certain color, I think you can change, I think it's marker fill. Marker face color. And we're going to make it red. Okay, we made a big red circle. Oh, look at that. Now we're just drawing the bob. Running it again. Any questions so far? We're animating a pendulum. We are controlling the pendulum. Not bad, right? Now, this is just drawing lines. You know, a single line, an O, a little circle because we have the O command. What if we want to have like a fancier looking pendulum? Okay. What if we wanted to make it look neater, where it's not just a line? Let's say it's just like, it's a larger, thicker thing with like kind of a rounded sort of edge. There, we can draw much more complex shapes in MATLAB. And I'll just show you how with just some real quick, with the fill command. We don't have a ton of time today. I'll tease the fill command for you all. So let's say you wanted to draw like this shape here. That this is the shape of your pendulum, of the stick of your pendulum. I don't know why you'd want it to look like this. Okay? And you wanted to color it in with a color. It's art class now. We're in art class. What you need to do, all you need to know, are the points of all these points, the coordinates of all these points, and you need the fill command. The patch command also works. It's slightly different, but it does functionally very similar things. This will be very helpful for your animations, for your homework. So let's say you know all these points. Right now I don't have time to go through all these points, but just say this one, this one, this one, this one. Let's say that the data points are that this here is 4, 2. This is 0, 2. This is 0, 0. And this is 4, 0. For the fill command, you say fill, and you have a list of all your X points. Just like you're plotting them for the plot command. And then all of your Y points in the order that you want to draw them. So let's say 1, 2, 3, 4. You don't have to, and it will draw these lines in order and then fill everything in the middle. Okay? So all of our X points are 0, 4, 4, 0, 0, 0, 2, 2. So this is 0, 4, 4, 0, 0, 0, 2, 2. Okay? I'll show you a real quick fill command on the screen. So I'm going to close all my plots. It says fill. I'll put in a vector of 0, 0, 4, 4, 0, and 0, 0, 2, 2. Let's make it a blue rectangle. There's a rectangle. It looks like a square. Let's do axis equal to show that it has it's a little rectangle that we just drew. That's it. And so if you are trying to plot a little cart for your homework, guess what? That's how you do a cart. All right. I know we're 1 minute over. I'll stick around for a couple questions. But that's the official end of the lecture. Thank you all so much. Thank you.